Hello everyone. Today I'd like to talk about high voltage isolators and the three main types of isolation technologies that are available in the market. An isolator is an electric component that transfers electrical signals between two isolated circuits, which are at huge voltage or potential difference. The optocoupler uses light to transfer electrical signals over the isolation barrier. The optocoupler has been used for more than 50 years, and it is still the most reliable and trusted source for isolation for most electrical system designers. The capacitive coupler and magnetic coupler, as the names imply, transfer high-frequency electrical AC signals over capacitors and magnetic coils. Over the past decades, these alternative technologies to the optocoupler have increased the high-voltage isolation performance by doubling the isolation structures to meet the high-voltage isolation requirements. Now, what will be very interesting is how good are these latest alternatives compared to optocouplers? We'll find out in this video with a quick test. Stay tuned. For this high-voltage surge test, I'm going to select the latest isolated sigma-delta modulators from Broadcom optocoupler, Isolator A optocoupler, Isolator B magnetic coupler, and Isolator C capacitive coupler. 3 units from each part number will be tested. The isolated sigma-delta modulator is specifically chosen because this state-of-the-art, high-accuracy shunt-based current sensor is usually used for phase current sensing and located between the switching power devices and the motor. High transient surge voltage occurs frequently during the acceleration, deceleration, and braking of the motor. Since the current sensor feeds back the phase current information to the microcontroller at the low voltage side of the system, galvanic isolation structure with significant high voltage isolation capability will prevent catastrophic damage to the low voltage system. I've prepared evaluation PCB boards with 2 isolated sides. Both primary and secondary sides of the PCB are powered by 9-volt batteries separately. The 9-volt is converted to 5-volt on each side of the PCB to power up the sigma-delta modulators. The differential inputs of the sigma-delta modulators are shorted to primary side ground. An ESD gun is used as the source for high-voltage surge. The ESD gun has a surge profile of very fast rise time of less than 1 nanosecond and a slow fall time of about 30 milliseconds. A single pulse surge voltage is applied to ground 1 on primary side of the PCB. Since the reference of the ESD gun is connected to ground 2 on secondary side of the PCB, the surge voltage will strike from ground 1 to the isolation structure and then return to ground 2. The surge voltage level is set to begin with 14 kilovolt. The output data of the sigma-delta modulator is monitored on the scope. If the output data continues to switch after the voltage surge, the isolation structure is assumed to be intact. The surge voltage level is then increased by 1 kilovolt. The test will continue at higher voltage levels until the output stops switching, or what we call latch up. Now let's have a look at some live video to give you a better illustration. Wow, did you see that? The Broadcom optically isolated sigma-delta modulator survives a 25 kilovolt high voltage surge across the isolation barrier. That's awesome. Not so lucky for Isolator B magnetic coupler. The output data latched and stopped switching at 14 kilovolt surge. The high voltage surge must have punched through the isolation barrier. Now let's take a look at the overall result. Broadcom optocouplers are the most robust against high voltage surge, whereby no failure is observed for all units under test up to 25 kilovolt test limit. Isolator A optocoupler outputs permanently latched starting from 16 kilovolt upwards, while Isolator B magnetic coupler from 14 kilovolts upwards and Isolator C capacitive coupler from 15 kilovolt upwards respectively. Although Isolator A, B, and C started to fail at about the same level, Isolator C recorded the widest range of the high voltage surge levels at which the test units failed. The high voltage surge will induce high density displacement current from ground 1 to the input circuitry of the isolator, and then transmit over to output circuitry and ground 2 via capacitive structures or parasitic capacitance formed throughout the isolation barrier. The diagram shows the various parasitic capacitance paths formed between the wire bonds of the input circuitry or input lead frame to the Faraday shield of the Broadcom optocoupler. The Faraday shield is grounded to ground 2 and provides an electric and magnetic shielding to remove the displacement current. In capacitive or magnetic couplers, the Faraday shield is not a viable solution. A Faraday shield would block the electric or magnetic fields used for data transmission in addition to transients. In addition to the Faraday shield, the Broadcom optocoupler lead frame and package design is optimized for smaller combined input-to-output capacitance, or in short, CO. The table shows the comparisons of CO of various isolators. With a smaller CO, smaller displacement current is included during occurrence of high-voltage surge. Thank you for watching. You now understand that to have a truly galvanic isolation that is able to withstand high-voltage surge, you will need to have an optical coupling Faraday shield and small input-to-output capacitance. I hope this helps in your selection of isolation components. Share your experience. Do you see what I see? Leave a comment here.